So we're officially in learning objective 4, the final learning objective. 3 more weeks of content, and then the content shuts off for this course. Which means, if we refresh, we have another homework, yay. So project 4 is out, so you can take a look at it, get an idea of what's being asked for this. I won't really go over it in depth right now, but as usual, we'll do test cases for the 3 tasks as we get there. So for this one, we are going to, I wouldn't say build a game, but the handout code has the structure of a game already set up. And then your task for this, as the name of the homework implies, enemy AI, you're going to get the AI to actually do AI kind of stuff. When you clone the repo and run this code, these AI characters, you're the yellow dot, the AI characters are blue dots. The graphics are phenomenal, I know. The blue dots will just kind of wander around aimlessly when you first start this app. Your goal is to get these blue dots to be able to hunt you down or each other. They won't distinguish between another AI character and you, so it'll be a big PvP basically with a bunch of AI, and they'll shoot at the closest player. When somebody gets sufficiently close to them, they'll start hunting them down and shooting at them. So that's what we want to build, and it's broken down into 3 tasks, which conveniently use our 3 data structures that we're going to learn. And then the last objective is finally getting the AI to be able to do some things, doing pathfinding with the AI. We want the AI, so if I'm right here and this AI character here is trying to hunt me, this AI should be smart enough to move around these walls, find me, and then shoot at me. That's what we want the AI to be able to do. Not just finding a path from here to here, but finding a path from here to here that avoids walls. That's eventually what we want to do and what we'll be able to build up to over the next 3 weeks. This mic is bugging me. So that's what we want to do for this homework. Is this game on Steam? Yeah, I'll hand out free Steam codes. It's on Epic Games. It's going to be on your laptop once you clone the code and finish the tasks. You can upload it to Steam. If you can make money off of this game, you know what? You have my permission to use my code. You can actually make money off of that. That'll be fine. If you slap graphics on there and tweak the gameplay a little bit so it's more compelling to play, it actually wouldn't be a terrible game. But it needs some work. It's pretty bare bones right now. So let's start learning what we need to learn about data structures. To do that, I keep forgetting to do this semester. I kept forgetting. But let me go up to the syllabus. Learning objective 4, data structures and algorithms. We're going to learn about 3 data structures, linked lists, trees, and graphs. 1 week each. And we're going to learn about the structure of each data structure. Today we're learning about the structure of a linked list. And we're going to talk about certain algorithms that we can use on a linked list. Actually, we talk about some algorithms today too. So we're not just focused on what the data structure is, how it stores data, how it structures its data, if you will. But also, what can we do once we have the data in that data structure? For linked lists, we got our data in a linked list. What can we do with it? Well, we've been using linked lists all semester. So we're really just looking at how the linked list we have been using actually works. For trees, I don't know what I'm trying to point to. For trees, we're going to see the structure of a tree and then things we can do with the trees. For the project, we're going to use a decision tree for task 2 and be able to decide what the AI is going to do. And it has 3 different actions it can take. It can just sit there and do nothing. And once another character is close enough to it, it will start hunting that character down. That's its second action, hunt. And then if it's close enough, if it's within range of its projectile, it's going to fire at that character. So 3 different things. It's got to decide how it's going to choose one of those 3 actions. We're going to use a decision tree for that. And then graphs. When we get to graphs, that's how we're going to get our pathfinding. We're going to represent that game board as a graph and use breadth first search, an algorithm that gives us useful information. For our purposes, we're going to use that to find the closest path, the shortest path to the target player. So that's what we're looking at for objective 4. I've said this many times throughout the semester, so this will probably be the last time I'll say it. The difficulty curve of the course in my opinion, I always got to qualify with this so somebody doesn't call me out at the end of the semester. Just like I said, one of the TAs said this AO was easier than the other ones, which many of you have told me they're full of it. But learning objective 4, in my opinion, is easier than learning objectives 2 or 3. There are no restrictions on the homework. You can use variables, you can use conditionals, you can use OOP, FP. At this point, you have tasks to complete, and it's up to you to decide what the best approach is for each problem, each task you're given. You got to write a method. Do I want to use recursion? Do I want to use classes and objects? Do I want to have objects that change state? Do I want immutable objects? It's up to you to approach it however you think is the best solution to the problem. So no more restrictions. We're done with restrictions. That was a tool banning conditionals to get you to force you to learn OOP, banning variables to force you to embrace functional programming. I don't need to do anything to force you to embrace data structures and algorithms. Just use the data structures, write some algorithms, and get the job done however you see fit. So that's another reason why the difficulty goes a little bit down for LO4, in my opinion. Feel free to disagree with me after you get through homework 4. But I don't imagine that changing. I think it's a pretty good step down in difficulty. I think the biggest difficulty in homework 4 is just reading and understanding the existing code and understanding what the hell my game is doing to know where your code fits into it. I think that's what students have the trouble with. Once it gets to writing the code, I'm not asking too much on homework 4. And I've said this before, again, last time. You have a lot of other projects, a lot of other exams. I've been kicking your ass all semester. Like, this is time for 116 to back off a little bit and let you focus on the other courses. If you made it through LO2, I believe is the threshold. If you made it through LO2, I believe you are going to pass the class. You're going to complete the class. And we're pretty well on our way through LO3. If you get through LO3, I'd say I'd bump that up to a certainty. You're almost certain to pass the class. You just got to finish off LO4. Very few students fail the class because of LO4. Very, very few. And when they do, it's usually just because they completely ran out of gas and have no energy left to be able to put any effort into LO4. It's usually the only reason somebody fails on LO4. So unless you get completely burnt out by this time, I'd say you're making it through 116 and getting to 220, 250. If you're surviving till this point, I'd say you're certainly doing that. Oh my goodness. Did I not download the slides yet? I don't think I did. Let's talk about some linked lists. More popular than Elden Ring? Yeah. I gotta get a bunch of streamers to play it. Let's go. All right, so let's talk about what linked lists are. Before that, just a quick recap on arrays and the difference between arrays and linked lists. I won't dwell on this comparison too much, but in 250, you'll learn all about this comparison. You'll talk about arrays, linked lists, trees, graphs, and all kinds of other data structures. Self-balancing binary search trees. Oh, man, it gets good. So I'm going to keep it pretty light on the comparison of data structures here. But an array, this was sequential in memory. So an array is just one big chunk of memory. And what you have, when you have an array, you don't actually have an array. You have the memory address of the first element of that array. That's what you get access to. And then if you want to access any element of that array, you take that memory address of the first element. That's what you actually have access to. And then you add the index that you're trying to search for. You want the value at index 30. You're going to take 30 times the size of each element. So if these are ints, you would times it by 32 bits. And then move to that memory address. You'd move to the, I'm saying it in bits, but it would be in bytes. I just don't want to say the wrong one. 4. I can divide, I promise. 4 bytes times 30. So you advance 120 bytes in memory, and that's where you would find the value of index 30. So with 2 operations, one multiplication and one addition, you can find the element you're looking for. This is very fast. This is what we call random access. It's very quick to find what you're looking for. In fact, our random access memory, our RAM, is just one large array with billions of bytes. That's all That's all RAM is a giant array. So everything we do, we kind of pretend that we have all these data structures, but they're all stored in an array. Even your hard drive is just a big array. It's a bunch of memory. It's a bunch of bytes of memory indexed by what position they are in that hard drive or in that RAM stick. So technically everything's an array. Every data structure is an array. We don't really think about it that way when we're coding, though, because that's not very helpful to us. Bless you. So this is fixed size. You cannot change the size of an array. If anybody tells you you can, they're lying to you maliciously. You can't change the size of an array. Once you have an array, you have to specify what size it is, and it will be that size for its entire life. Some languages have wrapper classes around arrays, so you can pretend like you're resizing an array, that you're adding to the end of an array. But what it's actually doing is once you run out of space and you try to add, once you fill up that array and you try to add another element, it's copying all of those values into a new array that's larger with more room, and then adding the memory to that new array. Can't change the size of an array, though, because it's one continuous block of memory, and you have no guarantee that the memory address right after the last element of your array is occupied or not. You have no control over that, and you can't ask the operating system, hey, give me this specific chunk of memory that's right after my array. You can't do that. The operating system's not going to let you specify which memory addresses it allocates to you. You just go to the operating system and say, I need this many bytes of memory, and then it chooses where in RAM that's going to be. Since we don't have control over that, our arrays cannot grow. Now, we could ask for an array that's larger than we need and then use up to that space, but we can't change the size of an array after we allocate it. Yeah, and Python lists is a dynamic array. Python lists, Java's array list, C++'s vector. These are wrapper classes around arrays that pretend that you can resize an array. So since that next byte of memory could be used by another program or whatever, maybe it's not even used by another program, but we have no guarantee of that memory. We have no control over it. So we can't resize our array. It's just not allowed. Linked lists, on the other hand, they're also a sequential data structure, meaning the order matters of the elements, but the values are spread all across memory. Now, I showed one linked list example earlier in the semester, so we got a small taste of what this looks like. But the values are spread all across memory, and then each value knows where to find the next value. So each value, which we're going to call linked list nodes, I don't know what I'm highlighting here, that we're going to call linked list nodes, know two pieces of information: the value that they're storing and a reference to the next linked list node in this list. So now if we want to navigate through a linked list, what we'll actually have is the memory address of the first node in the list, which we usually call the head of the list. And then that head of the list knows where to find the next node, which knows where to find the next node, which knows where to find the next node. And there's no rhyme or reason to where these nodes are actually stored in memory. They can be anywhere. They can be anywhere in memory. This does give us variable size, which we don't have in an array. We do have variable size because when we want to add a new element to a linked list, we just say, hey, operating system, give me enough space to store one element of my data type and a reference. We get that somewhere, anywhere in memory, and then we update the references to add that to the list. So we can always add, increase and decrease the size of the list. We can add elements, we can remove elements, we can do all that good stuff. So, and I was looking at these slides a little too late. I didn't revise these for the new format of our memory diagrams. But we can still see the idea of what's happening here. By the end of the week, I'll do the new memory diagram. I'll do an example. But we'll have, where do I want to start? But we'll have a list. In our stack frame, we'll have a reference to a specific linked list node, which I'm still not calling linked list nodes in my slides. So the reference 506, and that node is going to store the value 5 and have a next, which is going to be another reference, which is the value 775 in this, which is, again, the 506, 795, and 416. Completely made up numbers. I just made up these. They could be anything as long as they match what I'm referring to. So the next is 785, some completely different location in RAM in my heap. That has the value 3 and a next of 416. So that takes us to here, which has a value of 1. And for this next is going to be null. Null in programming means nothing. There's nothing there. It refers to nothing. So whenever we see a next of null, that's how we're going to indicate that this is the end of our linked list. Now, I have to add a disclaimer here. Scala developers really don't like us using null. It's just kind of counter to the culture of Scala development. I say, whatever. We're going to do it because it keeps things a bit simpler for these. But I have a better reason for that. In 220, you're going to see null termination, which is a very C thing. 220 is in C, if you haven't heard that yet. It's a very C thing to do of how to know that you've reached the end of an array. You put right after the last element, you put a null character there, and then you constantly check for null to see if you reach the end of the list. So if we're using null here, or the end of the array in that example. So if we're using null to end our lists in 116, it's going to give you a little heads up of when you're going to see it in 220. You're going to know what that means. Null termination, that's what we're doing here. Linked lists are null terminated. Whenever we see a reference to null, that's the end of the list. And then in our code, we'll say if next equals null, then we know we've reached the end of the list. Yeah, 220 is in C, if that's the question. Does a node just store values? A node stores the value and a reference to the next node. So this list, if I have this list on my stack, the way we would always think about this before we cared about what a linked list actually is and how it's represented in memory, this list has the values 5, 3, 1. So this is a list that has the values 5, 3, 1 in that order. Is Project 4AO harder than Project 2 and 3's? This one I will say, again, in my opinion, but I don't think I'll be challenged on this one. The Project 4AO is easier than either the Project 2 or Project 3AO. The Project 4AO isn't much of a step up in difficulty from Task 3 of the project. And for both of them, I have a lecture where I pretty much walk you through the whole thing and explain to you exactly how to do it. If you can do Task 3, you can do the AO. So don't leave that AO on the table for homework 4. Yeah, 220 is just in C. I was going to ask you about that. Did they add C++ to 220? I wouldn't think they would. Yeah, null termination is a big thing in both, though. Will we be tested on first-order functions in the written part of the quiz? No. It's been asked and answered quite a few times. All right, so in the code, this is what it's going to look like. Our entire linked list node class, at least to start, is just this. Then we're going to add methods to it when we learn about more algorithms. And then if you look in the repo, it has a whole bunch of algorithms in there. But our linked list node, that's it. Takes a type parameter, as our data structures do. If you create a Scala list, you want to create a Scala list of a specific type. We want the same thing, so we're going to take a type parameter A, which can be anything. We can have a linked list of whatever. We're going to store the value, which is an instance of A. So if we have a linked list of ints, give me an int. Each linked list node has to have an int to refer to. And next, and does it feel good to see var again? I like seeing vars again. Next, which is going to be an instance of a linked list node, which is the next node in the list, which may or may not be null. And then I can create a linked list to use this class. This is the entire linked list node. This is all we need to create a linked list. And to create it, I'm going to create new nodes. This linked list node that I create has the value 1 and refers to null as the next element in the list. So this, we have a list containing just the value 1. It's just one node in the list. Then I'm going to create another linked list node with the value 3 that refers to whatever my list stores. My list is right now a reference to this list containing just the value 1. And then I'm going to reassign that to my list. So my list equals the node with the value 3, and next equaling this node with the value 1 with a next of null, which is the end of the list. And then do it again with the value 5. So now my list refers to a node with the value 5, which refers to a node with the value 3, which refers to a node with the value 1, which refers to null, indicating the end of the list. This is a mutable list. So this implementation is different than the Scala list, which is immutable. So this is a mutable list. We can change the values in this list, and we can change the elements in the list without creating a brand new copy of the list, because that is quite a bit more difficult to set up. I believe they still build immutable lists in 250. I'm not 100% on there. Now that the instructors have been shifting in and out of 250, I'm not sure where they settled on immutable lists in 250. I think they used to do immutable lists and immutable trees at one point, but I don't know if they do at this point. Can you use 4AOs on Project 4AO? You can't use ROs on any application objectives. And if you're talking about the tasks, yeah, you can't extend your deadlines indefinitely, because at some point I have to put in final grades. So like on task 3 of Project 4, you can't use all 4 of your recovery opportunities because you wouldn't have it done before I have to put in final grades. So we do have a practical constraint there. So the Wednesday of finals week is the latest you can extend. All right, so let's walk through this and see how this would work in the heap. So at first, my list is going to store the reference 416, which refers to a linked list node on the heap with the value 1 and a next of null. On this next line, we're going to create a new linked list node with the value 3 and the reference 416. It's taking my list. My list at this point in time referred to 416. So next is going to be that reference 416. And we have the value 3, and then reassign it to my list. My list is going to have that value, the reference 795. I might have to redo this example with the new, actually I will exactly have to do this, with the new memory diagrams that you have to do for your quiz. And now I'm realizing why we made that switch. This is a little confusing, isn't it? And then we hit another one. My list, create a new linked list node, 5 in my list. My list at the time stored 795. Those are our constructor parameters, our state variables. And this is going to return whatever reference this new linked list node has. And that's going to be reassigned to my list. So we're building this list one node at a time, and then always storing a reference to the head of the list or the first element of the list. And I'm building this in reverse order, which is the same way that we would think of prepending. I'm prepending 3 to this list. I'm prepending 5 to the list, and then getting that list 5, 3, 1. And that's all actually, let me leave this slide up for a bit. That's all I want to talk about with the structure of linked lists. There's not a whole lot to it, especially if you have a firm grasp on stack and heap memory and references. We're going to create nodes that have a value and a next. Next is the next link, the next node in that linked list. And then we can have these spread out anywhere in memory. I just have 3 random memory addresses here where the list is stored. And these can be anywhere in memory. We don't care where they are. It's not important to us. All that we know is, and all we care about is that we have a reference to the first element of the list. And that element knows where to find the next element, which knows where to find the next element, which knows where to find the next element, which knows where to find the next element, et cetera, et cetera. Until we see a next of null, then we know we've reached the end of the linked list. So, are there any questions on the structure of a linked list? Yes?
So, when you're making this class linked list,
Mm-hmm.
the second variable is of type linked list. That's, like, we know that's going to be a reference, right?
Mm-hmm.
Is that why you can give it null in the first? Like,
So null's a dangerous thing to work with. You can, we can give this null in replace of a reference, and that's valid. It's, in a lot of instances, it's frowned upon. Like the Scala community says, just don't use null ever. Use something else. But they still put it in the language, so I'm going to abuse that. But whenever you have a variable of a type that's supposed to have a reference, it could always be null. So theoretically, we could check in all of our code everywhere. Like we have errors everywhere in our code because we're not checking for null. Theoretically, we should say, if this equals null, do this, else actually do the thing. We could put that everywhere because we could have test cases that check for null. Like, let me give this method null. Oh, it broke. Failed the test. Like, we could do that all the time. This is always valid to put null in place of a reference. We don't like to, though. And I've never talked about testing edge cases with null for good reason. It's just like one extra test case you'd have to write, one extra line in your code, if null, do this. But out there in the real world, you're going to see cases where like you'll have to actually do that. You have to check for null in your inputs. Did that answer your question?
Yeah, it did.
Okay. So I want to comment on LO quiz 3. Are we having 3 questions or 2? Never mind. Oh, that's easy to answer.
Well, no, because it was like asked before, but
yeah, two questions. So I get it is still ambiguous. So there won't be a question on functions, but like we could have 2 recursion questions. But no, we're going to have 1 recursion and 1 immutability question.
Okay. Thank you very much.
Yep, no problem. 2 topics and 1 question per topic. Yeah, the idea was like each learning objective would have 3 quiz questions, but that kind of fell apart pretty quick. Even for LO2, LO2 could have had an immutability and a polymorphism question, but we ended up rolling them into 1. Partly because those get so messy. There's like having you go through the tedium of doing it twice would be quite a bit. Immutability for the AO. I don't know how to answer that question. Immutability for the AO. I don't know if I can even interpret that in a way that makes sense. I need some more words on that one. My mind is on homework 4, so I'm thinking homework 4 AO. I think you're referring to homework 3 AO, which, yes, you have to use immutability. All of homework 3 you have to. Immutability. Oh, for the quiz. We're still talking quiz. Yeah, AO is so ambiguous. So the AO on a quiz is never associated with a specific question. Like there's the idea that we have, like we could have a hard question, which is the AO question, but we really haven't done that this semester. We haven't done that in practice. It's here are the questions. If you do pretty good on them and show that you understand what we were putting down in class, you'll get the LO. And if you really got every point that we covered and have a really high understanding of what's going on, and you have maybe no mistakes or just very minor mistakes, then you get the AO. It's not on a per question basis. It's not like this question is the LO and this question is the AO. That's just not how we do the grading. The LO is like, well, you got some mistakes, but they're not critical to your understanding of this topic. You can get through that. AO is like, yeah, you understand what's going on here. And your only mistake was like not adding the stack frames for your methods that just print to the screen. That would be acceptable since I made that mistake. The TA asked questions on syntax during the interview. Oh, will they? I thought that was a statement. Like, they ask questions about syntax? I would have been upset. No, they should not be asking questions about syntax. The only time they'll ask about any syntax is like for keywords. Like for OOP, what do the keywords this and extends and override mean? Like, those are all valid questions. But what's the syntax for recursion? Like that, I don't know if that question makes sense. The whole idea of the interview is that we want you to understand the concepts, the underlying concepts. In the homework, that's where we're testing your syntax. In the quiz, we're kind of implicitly testing your syntax. The interview should be at a conceptual level of seeing if you can have a conversation about that specific topic. Because that's what you'll do in your careers. Like, you have to talk to your coworkers about OOP. Like, it's something that you have to do. Yep.
Back to the null and the reference thing.
Mm-hmm.
But null is unique in that way, right? You couldn't pass that another specific reference. That's just some random other object on the heap, right?
Yeah, it would have to be something. It would have to be a linked list node at some level. It could be polymorphism, so it might not be a linked list node, but it had to have to be something that extends linked list node at some point. It would have to be all the OOP. And then null, and I think none works as well. On the inheritance tree, when I show that, like none is at the bottom that extends everything. You could use none. I forget the exact syntax for that. Use none. But null is a keyword in the language, so it's treated very specially. Which is why Scala devs don't like it. We don't like things that are Scala devs don't like things that are special cases. Oh my goodness. All right, I'm not answering any more questions that are on this syllabus. Let's move on. All right, we've been on that slide long enough. Everybody's familiar with the structure of a linked list. Hopefully that's looking all right, because I'm going to use that structure, and we're going to talk about some algorithms. So now that we know the structure of a linked list, we want some things that we like to do. If we have a list, sometimes I want to ask that list, what's your size? How many elements do you have? Maybe I want to print all the elements in the list. Maybe I want to get an element at a specific location, something we've done all semester. We would have our list, and then in parentheses, some number. Give me that index. There's no indices with lists, but I'll still call them indices. But we pretend that they have indices by saying, give me the value at index 4 or the 5th element of the list. We want to do that. It's something we like to do. We want to add and remove elements, and we want to find a specific value. Does this list contain a specific value? Things like that. We like to do all these things. So let's just do them. I'm just going to go through them one at a time and show you how we would do these things. And again, these are all in the repo in the linked list node class. So if I want to compute the size, I'm going to do it like this. Now, I'm going to show recursive examples for each of these, because now we know what recursion is, and I want to reinforce recursion. And I'll have more to talk about that later, but I'm going to show you the recursive examples for each of these. So to get the size, you could just write the same code as a loop. Well, next not equal null. Well, node.next not equal null. Node equals next size plus plus, or not in Scala, but plus equals 1. The recursive solution, the base case is going to be next equals null. That means I have a linked list node, which is the last node in this list. And I know that I have a list of size 1. If I'm not at my base case, I'm going to make my recursive call on the next element of the list. And this is in the linked list node class. So this is a reference to a linked list node. And this method is initially called on the head of a linked list. So I'm going to get the size of the next node. So if I'm a node in a linked list, what I'm going to do is ask my next node, hey, next node in the list, what's your size? That node's going to tell me, hey, this is my size. I'm going to add 1 to it and then return that to the node that asked me the same question. So the base case, we have a node at the end of the list that says, I don't have a next element. I'm the end of the list. I'm a list of length 1. Return that to the next node. And then each node adds 1 and then returns. Add 1, return, add 1, return. By the time we get to the head of the list, we're going to have the total size of the list, since every node in the list added 1 representing itself. It's basically like taking taking attendance or something. Every node is like, here, I'm here, I'm here, I'm here, I'm here. And then the head can return to whoever asked about its size. Hey, here's the total size of the entire list. Or we assume that this is true. If this is correct, if that's correct, my next node size plus 1 must be the size of the list that I refer to. So and the crucial part here is no linked list node knows very much. It knows its value, and it knows a reference to the next link in the chain. And that's it. So to get anything really working, we either need loops or recursion. I'll use recursion, but we're going to make a recursive call and say, hey, next element, give me some information, by going all the way down using recursion, and then we can compute the rest by adding 1 in this case. And this is how our linked list methods will look for the most part. Are we at the end of the list? We do that by checking if next is null. If we are, handle this as a list of length 1. Else, do our recursive step. Make a recursive call and just process this particular node. ToString. Sometimes we want to print out the values of a list. If we print out a Scala list, we'll get the actual elements of that list printed out because it has an overridden ToString method. We want to do the same thing with our linked list node. So we're going to check, is this the end of the list? If this is a list of length 1, we're just going to ToString whatever our value is. Now remember, our values are type T. It's just any type ever. We don't know what type it is, so we can't use any specific functionality that's specific to any particular type because we don't know what type it is. But we have one key advantage here. The any type in Scala is what implements the ToString method. So every object in Scala has to have a ToString method because everything extends any. So we always have a ToString method. So even when we have a type parameter, we can actually still call ToString on that type because it doesn't matter what type it is. It has a ToString. Everything has a ToString. Everything has a ToString. Everything has an equals method. Everything has a hash code, which isn't very useful in this class. But there are a few methods that absolutely everything has. ToString is one of them, so we can actually call ToString. We're going to convert our value to a string and return it. If we're in the recursive case, we're going to call next ToString. We're going to call ToString on this element. We're going to slap a comma right in the middle there. So if this is the entire list after this node, represented as a comma-separated string, if that returns the right value, we're going to prepend our values ToString and put a comma in between, and we're good. We got our ToString method. And this is a nice way to handle the commas, too. This is easy with recursion. We want a comma added for all but the last element. Well, we're already treating the last element as a special case, as the base case of our recursion. It's easy to only add the commas where they're necessary. You do this in a loop, and you need a little extra logic. OK, if next equals null, don't add the comma, else add the comma. It's just a little bit more code. It's one case where it's easier to write the recursion than the iterative using a loop to get these commas right. This will get the commas right because we're only adding the comma if we're in between two values. Oh, I meant to remove this slide. I'm not doing the debugging demo today. We got enough to cover in the slides. All right, so let's talk about accessing a value. I'm going to use the apply method. This is, if you do dot apply on your list, this always causes some confusion. Dot apply and then some value, that's the same as just using parentheses on your list. So if you have your list and then in parentheses some integer, give me the value at index 4. Or if you do dot apply of 4, those do the same exact thing. In fact, the parentheses, the only thing that does is calls the apply method. It doesn't, they're not two separate methods, they're not two special things. All it does is call the apply method. So if I do apply of 4, this is where we really get to see some of this pain of a linked list if we don't use them properly, or if we don't use them efficiently, I should say. Apply of 4 is the same as calling this dot next, dot next, dot next, dot next. There's no way we can just jump to the 5th element of a linked list the way that we can with an array. We can only do that because arrays are one continuous block of memory, and we can mathematically compute where the value at index 4 will be. We can't do that in a list. There's no magic that we can do to just come up with where that element will be, because it could be literally anywhere in memory. Anywhere in heap space it can be. We have to start at the first element, jump over to the reference of the next element, jump to the reference of the next element, and just keep going one step at a time. So if we want to get the millionth element out of a linked list, we have to make 1,000,000 jumps all around memory, constantly jumping around your RAM to be able to get to that millionth element. This is an O of n runtime call because we have to navigate through all of memory to be able to find that nth element or ith element. It's a very slow operation. This is why when I was talking about selection sort, I said these calls to apply of I or apply of j, those are very slow operations, and this is why. It has to jump all around memory to be able to find that element. Very, very slow operation on a linked list just to get a random value out of this linked list. Very, very slow. In the code, if I equals 0, we've reached the node that we want. Else, make the recursive call with I minus 1. So we're trying to call next I times. So if I call next once, then the next node's job is to call it I minus 1 times. And there's my recursion to handle that. Very, very slow operation. All right, let's add an element to this thing. We have a list 4, 3, 1 null. So a list with values 4, 3, 1. And say we want to add the value 2 in this list right after the value 3. So right here, I want the value 2. That's my goal. So I can get 4, 3, 2, 1. What I need is a reference to the node before the location that I want to add this. So if I have a reference to this node, I can add something after this node because I need access to its next variable. We have to have a reference to this node, and we're going to update. We're going to create our new node with the value 2. We're going to update next to refer to the new node we just created, and whatever this node used to refer to, which is this node, that's what the new node's next has to refer to. So the way we insert or remove elements from a linked list is by creating the new element if we're inserting, and then updating the next references to be able to get the values in the right order that we want. So we're creating the new node and then updating a couple of nexts to be able to get this node structure the way we want it to be. In the code, this is super simple. We want to insert an element. Again, this is in the linked list node class, so this is a reference to the node that we're adding the element after. We're going to create a new linked list node with the new value we're adding. Its next is going to be whatever this node used to be referring to. And this node's next is updated to a reference to that new linked list node. And that gives us all the functionality we just saw visually on the previous slide. If we want to delete a node, so maybe that was a mistake. We didn't want to add 2 there. We want to remove that node now. To remove a node, we need a reference, just like inserting, we need a reference to the node that comes before it. And removing a node is even easier than adding a node, assuming we have a reference to the node that we want to, before the node that we want to delete. We're going to update next to the next node's next. So we're just going to update this next to cut this node that we're deleting out of the picture completely. Now that node still exists. This node with the value 2 and a next of this node with the value 1 still exists, but we just don't care about it anymore. We just kind of let it sit there and not do anything. We don't have a reference to it anymore, so it'll end up getting garbage collected. But this list, this node, effectively isn't in the list and doesn't exist anymore, even though it still does exist in memory and refers to this node. So that's all we have to do to delete an element. If we want to delete the element after a particular node, this .next is the node we want to delete. Whatever its next is, well, that's now this node's next. So we just cut that node out of the picture completely. It's not part of the list anymore. In the memory diagram, would we have to cross out the node which isn't referenced? This is an excellent question. No. It's OK if you do, and it's OK if you don't. Paul did in his section, and then I didn't last Monday when I could have. That was my chance to show you that, and I didn't with immutable objects. So either way, we're going to accept either way since we show their sections different ways to do it. When does that deleted node leave memory? That's a good question, too. We don't know. It'll get garbage collected at some time at the JVM's discretion. Whenever the JVM decides to garbage collect it, that's when it's garbage collected. We have no control over that, and we don't really care when that happens. When are L2 second chance grades coming out? They'll be out shortly-ish. They're being worked on. There's I have a TA meeting tonight where I got to talk to them, and I'll have a better answer after that. You either have your grades by Wednesday, or you can ask on Wednesday, and I'll have a better answer for you. To find a value, where are we? 348, 349. I can save this for next time so I can get to the thing. Map, I don't really want to talk about at all because it's a bit too much for each. Yeah, let's leave it at that so we can do the lecture question. I'm sick of doing these lecture questions after the end time. Paul and I had a debate over this one. I think there's no right answer to this question, but he's arguing that there is a right answer.
So you're telling me that if I do get it wrong, I'll still get credit?
Depends what you say, I guess.
So you're telling
And
me,
what your argument is. If you get this wrong, you can email me and make your argument, or come to office hours.
so you're telling me not to put D?
Not to put D?
Yeah.
I don't know. I think there's a good argument that D would be a true statement. Paul disagrees. He thinks we're sometimes not evil, but I don't know. I think it's ambiguous. I think you can make an argument that D is a true statement. I think that's why he put all the time in bold. He said there was one instance where he wasn't evil. Have a great day. I'll see you Wednesday.